Here is a combined summary of the 2 pages. This research focuses on developing a novel preconditioned method for solving space-fractional diffusion equations, which builds upon an ideal preconditioner pioneered in Pestana, 2019. The linear system resulting from standard discretization is a non-symmetric, multi-level Toeplitz system. By applying a simple symmetrization strategy, the original system is transformed into a symmetric multi-level Hankel system. A symmetric positive definite multilevel Tau preconditioner is proposed for the symmetrized system, which can be efficiently implemented using discrete sine transforms. Theoretically, mesh-independent convergence is demonstrated when employing the minimal residual method. The eigenvalues of the preconditioned matrix are proven to be bounded within disjoint intervals containing plus or minus 1, without any outliers. This work addresses the growing interest in developing effective preconditioners for symmetrized Toeplitz systems, which stems from 32. The symmetrization strategy involves premultiplying the original non-symmetric Toeplitz matrix with the anti-identity matrix, enabling the use of the minimal residual (MINRES) method. While generalized minimal residual (GMRES) method is commonly applied to original non-symmetric Toeplitz systems, its preconditioning is largely heuristic, and its convergence behavior cannot be rigorously analyzed solely through the knowledge of eigenvalues. In contrast, various preconditioning techniques have been proposed for symmetrized Toeplitz matrices, including absolute value circulant preconditioners, Toeplitz, and band Toeplitz preconditioners. This research explores the effectiveness of Tau preconditioners for symmetrized Toeplitz systems arising from discretized fractional diffusion equations, specifically the space-Riemann-Liouville (RL) fractional diffusion equation. Here is a combined summary of pages 3 and 4 of the research paper. The paper discusses a numerical method for solving a multidimensional space-fractional advection diffusion equation with a source term. The equation is defined on an open hyperrectangle domain omega with a given function u0, x, and non-negative diffusion coefficients d, plus or minus. The left and right-sided Riemann-Liouville fractional derivatives are used to model the space-fractional derivatives. A backward Euler method is applied for the temporal derivative, and the shifted Grunwald scheme is used for the space-fractional derivatives, resulting in a first-order accurate scheme in both time and space. This leads to a linear system ANUK equals nu UK1 plus FK, wherein is a non-symmetric multi-level Toeplitz matrix. The matrix N is expressed as a sum of Kronecker products of identity matrices and Toeplitz matrices L, alpha I, Ni, which are generated by complex-valued functions G alpha I, theta. The generating function of N is given by F alpha, theta, equals nu plus N Airy summation I equals 1 dV, plus G alpha I, theta I, plus V, G alpha I, theta I. Instead of solving the original system, the MINRES method is employed to solve the equivalent system ANUK equals YN, nu UK1 plus FK. The authors aim to find an effective preconditioner to expedite the convergence of the MINRES algorithm. However, they note that circulant preconditioners are not suitable for ill-conditioned Toeplitz systems and multi-level Toeplitz systems, and band Toeplitz preconditioners are not applicable for the matrix EN and due to the fractional order of the zero in the generating function F alpha. The author's goal is to develop a novel preconditioner that can efficiently solve the symmetrized system EN equals YNB. The discussion sets the stage for the introduction of a new preconditioning technique that can tackle the challenges posed by the multi-level Toeplitz matrix EN. The authors discuss the challenges of preconditioning non-symmetric multi-level Toeplitz systems, particularly in the context of space-fractional diffusion equations. They highlight the limitations of the ideal preconditioner proposed in 31, which, despite facilitating fast MINRES convergence, is computationally expensive and lacks theoretical justification. The authors' primary contributions are twofold. Firstly, they prove that the ideal preconditioner can indeed lead to a MINRES convergence rate independent of the mesh size. Secondly, they propose a novel multi-level Tau preconditioner, denoted as PN, as an improved alternative to the ideal preconditioner. This preconditioner balances effectiveness with computational feasibility, offering a practical strategy for preconditioning fractional diffusion equations and achieving mesh-independent MINRES convergence. The authors define the tau preconditioner Pn in equation 2.4, which involves the symmetric part of the multilevel Toeplitz coefficient matrix and the tau matrix approximation. They utilize the diagonalization property of the tau matrix, expressed in equation 2.2, to efficiently compute the product of Pn and a given vector in O, n log n, operations using discrete sine transforms. The eigenvalues of the preconditioned matrix Pn(1) enon, where enon is defined by equation 1.7, are proven to be contained in a disjoint interval enclosing plus or minus 1. This result guarantees theoretically mesh-independent convergence when MINRES is applied. The authors also demonstrate the effectiveness of their proposed preconditioner through numerical examples in section 5, supporting the theoretical results concerning the eigenvalues of the associated preconditioned matrices. The proposed multilevel tau preconditioner Pn is shown to be diagonalizable by a d-dimensional sine transform matrix, enabling efficient computation of the product of Pn and a given vector. The authors argue that their approach offers a practical strategy for preconditioning fractional diffusion equations and achieves mesh-independent MINRES convergence. Multilevel Toeplitz matrices are defined as $T_n f equals sum_j_1 less than n_1 c dots sum_j_k less than n_k j_1 caret n_1 o times c dots o times j_k caret n_k a j dollar, where $a j equals frac 1 2 pi caret k int underscore pi caret k f theta e caret I Langle j theta rangle d theta dollar are the Fourier coefficients of a generating function $f in L_1 pi caret k dollar. The matrix $j_j caret n dollar is defined as the $n times n dollar matrix whose $l h $th entry equals 1 if $lh equals j dollar and 0 otherwise. Multilevel Toeplitz matrices have various properties, such as being Hermitian if the generating function is real-valued, and Hermitian positive definite if the generating function is real-valued and non-negative. Multilevel Hankel matrices can be defined similarly as $h_n f equals sum_j_1 equals 1 caret 2n_11 c dots sum_j_k equals 1 caret 2n_k1 k j_1 caret n_1 o times c dots o times k j_k caret n_k a j_1 l dots j_k dollar, where $k r in math bb r caret r times r dollar is the matrix whose $I j $th entry is 1 if $I plus j equals k plus $1 and 0 otherwise. A multilevel Hankel matrix is symmetric. The permutation matrix $y_n in math bb r caret n times n dollar can be used to symmetrize multilevel Toeplitz matrices, such that $y_nt_n f dollar is a symmetric multilevel Hankel matrix. The asymptotic spectral distribution of $y_nt_n f dollar is crucial for developing effective preconditioners, and has been established for the unilevel case and generalized to the multilevel case. Two useful lemmas are provided, including lemma 4.1, which states that for non-negative numbers $xi_i$ and positive numbers $zeta_i$, it holds that $min_1 lec I lec m frac xi_i zeta_i lec frac sum_i equals 1 caret m xi_i sum_i equals 1 caret m zeta_i lec max_1 lec I lec m frac xi_i zeta_i dollar. Lemma 4.2 provides the generating function of a matrix $et_m equals C_1 L alpha_m plus C_2 L alpha_m top dollar, which is given by $f_alpha theta equals frac 2 sin theta 2 alpha C_1 plus C_2 cos frac alpha 2 pi theta plus theta I C_2 C_1 sin frac alpha 2 pi theta plus theta dollar. The convergence result of the ideal preconditioner H n is presented, where H n is defined as n plus a n 2. Lemma 4.3 establishes that H n is symmetric positive definite, ensuring the preconditioning effectiveness of H n for the system X equals YNB. This is proven by showing that H n can be expressed as a sum of symmetric positive definite matrices. Lemma 4.4, adapted from 31, Theorem 4.2, provides a bound on the eigenvalues of H n minus 1/2 in n minus 1/2, which lie in the intervals -1 minus e minus 1 union 1 plus e. The parameter e is defined as the essential supremum of the ratio of the imaginary part to the real part of the function f alpha theta, which is a key component of the preconditioner. Proposition 1 provides an upper bound on the essential supremum of the ratio of the imaginary part to the real part of f alpha theta, denoted as s up theta element of minus pi d im f alpha theta re f alpha theta. This bound is expressed as max 1 is less than or equal to I is less than or equal to d plus minus d plus d minus tan alpha I 2 pi. The proof involves analyzing the real and imaginary parts of the function f alpha theta and applying lemma 4.1 to estimate the desired ratio. The analysis on page 10 further develops the bound on the essential supremum of the ratio of the imaginary part to the real part of f alpha theta. By examining the real and imaginary parts of the function g alpha I theta I plus g alpha I minus theta I, the bound is established as v plus minus v minus v plus v minus tan alpha I 2 pi. This bound is then used to derive the final result, which is presented as the maximum of this bound over all I. The proof concludes by establishing the desired bound on the essential supremum of the ratio of the imaginary part to the real part of f alpha theta. Proposition 2 establishes that the eigenvalues of H n minus 1 in lie in minus 1 plus e minus 1 union 1 plus e, where e is a function of the matrix n. This result, combined with proposition 1, implies that the eigenvalues of H n minus 1 in n are contained within disjoint intervals minus beta union beta with no outliers, ensuring optimal convergence of the MINRES method. Specifically, the kth residual of R k satisfies parallel R k parallel 2 parallel R 0 parallel 2 is less than or equal to 2 beta minus 1 beta plus 1 k 2. By setting beta equals 1 and beta equals 1 plus e, corollary 1 follows, stating that the MINRES method for the preconditioned system 1.7 has a convergence rate independent of n. The residuals generated by MINRES satisfy parallel R k parallel 2 parallel R 0 parallel 2 is less than or equal to 2 omega k, where omega is a constant independent of n defined as omega equals re 2 plus e, with e given by proposition 2. The proposed practical preconditioner Pn is introduced, and lemma 4.5 guarantees its positive definiteness. Lemma 4.6 states that the eigenvalues of tau h l alpha m minus 1 h l alpha m lie in 1/2 3/2 for alpha element of 1 2 and m greater than 0. Proposition 3 shows that Pn and H n are spectrally equivalent, with the eigenvalues of p-1 nanohenry, and, lying in, 1/2, 3/2. This result is established by combining lemma 4.6 with the Rayleigh quotient theorem. The spectral equivalence of Pn and Hn implies that the preconditioner Pn can effectively replace Hn in the MINRES method, ensuring optimal convergence. We establish the preconditioning effectiveness of Pn for Enan through theorem 4.1, which states that the eigenvalues of p-1 NYNAN lie in the intervals -3/2, 1 plus e, -1/2, union, 1/2, 3/2, 1 plus e, where e less than max 1 is less than or equal to I is less than or equal to d, plus minus d, minus d, plus d, minus tan, alpha I, 2 pi. To prove this, we utilize lemma 4.7, Ostrowski's theorem, and propositions 1 and 3, which provide bounds on the eigenvalues of p-1/2 nanohenry, and p-1/2 n and h, and -1/2 e nan, and -1/2, respectively. These bounds lead to the conclusion that lambda k, p-1/2 NYNAN p-1/2 n, equals theta k lambda k, h, and -1/2 e nan, and -1/2, where theta k is a positive real number. The disjoint intervals, -3/2, 1 plus e, -1/2, union, 1/2, 3/2, 1 plus e, imply that mesh-independent convergence can be achieved using MINRES. Specifically, Corollary 2 states that the residuals generated by MINRES for the preconditioned system satisfy parallel R, K, parallel 2, parallel R, 0, parallel 2 is less than or equal to 2 omega, K. Where omega is a constant independent of n defined as omega equals square root 2 plus 3e, 4 plus 3e, element of 1/2, 1. The eigenvalue bounds and convergence rate are crucial for understanding the preconditioning effectiveness and efficiency of the proposed method. The numerical experiments in Section 5 demonstrate the effectiveness of the proposed preconditioner against the state-of-the-art preconditioned MINRES solver proposed in 31. All experiments are carried out using MATLAB Art 2023b on a Mac Studio. The results of these experiments will be presented in the following sections, providing insights into the performance and efficiency of the proposed method. The proposed preconditioner Pn is implemented using the discrete sine transform function in MATLAB and is compared to existing ideal Toeplitz preconditioners AR and AM from 31. The MINRES solver is used with the identity matrix, Pn, and multigrid approximations of AR and AM, denoted as minresult, Pn, Mg, AR, Mg, AM. The numerical tests are conducted on a unidimensional fractional diffusion problem with zero initial condition, where the parameters h and tau are chosen to ensure a constant nu throughout the computations. The first test examines the performance of the preconditioners for different fractional derivative orders, alpha equals 1.1, alpha equals 1.3, alpha equals 1.5, and alpha equals 1.9. The results in Table 1 show that the iteration count for minres Pn remains stable across different values of alpha as the spatial grid is refined, requires less CPU time than MINRESMG, AR, and MINRESMG, AM, and demonstrates an improved preconditioning effect as alpha approaches 2, consistent with Theorem 4.1. Figures 16 display the eigenvalues of Pn1 Enan for various values of alpha and n, confirming the presence of a disjoint interval predicted by Theorem 4.1 and the improved preconditioning effect as alpha approaches 2. Table 2 examines the impact of diffusion coefficients d1 plus and d1 on the performance of the preconditioners, showing that the difference, d1 plus d1, affects the convergence, not the individual values themselves. The results indicate that the proposed minres Pn outperforms both MINRESMG, AM, and MINRESMG, AR, in terms of CPU times, while all preconditioners demonstrate optimal performance in terms of iteration count. The CPU time for minres Pn does not scale properly with n, potentially due to the limited size of n. The tables on pages 17 and 18 present the results of the MINRES algorithm for solving non-symmetric linear systems, with a focus on its performance for different values of the parameters alpha, d1, plus, and d1. Specifically, Table 1 shows the iteration numbers and CPU times for example 5.1, where the system matrix is a Toeplitz matrix with alpha equals 1.1, n equals 511, d1, plus equals 1, and d1, equals 10. The results are presented for different values of alpha, ranging from 1.132767 to 1.932767, with corresponding iteration numbers and CPU times for the MINRES algorithm with and without preconditioning. The eigenvalues of the matrix EN are plotted in Figure 2, which shows the clustering of eigenvalues around the origin, indicating the effectiveness of the preconditioner. The results in Table 1 demonstrate the efficiency of the MINRES algorithm with preconditioning, as it achieves significant reductions in iteration numbers and CPU times compared to the unpreconditioned case. Table 2 presents the results for example 5.1 with alpha equals 1.5, where the system matrix is a non-symmetric two-level Toeplitz matrix. The results are presented for different values of the parameters d1, plus and d1, ranging from 1, 1, to 9, 9. The iteration numbers and CPU times are reported for the MINRES algorithm with and without preconditioning, as well as for the preconditioned case with the PN preconditioner. The results in Table 2 demonstrate the robustness of the MINRES algorithm with preconditioning, as it achieves consistent performance across different values of the parameters d1, plus and d1. The preconditioner PN is shown to be effective in reducing the iteration numbers and CPU times, especially for larger values of the parameters. Overall, the results presented in Tables 1 and 2 demonstrate the effectiveness of the MINRES algorithm with preconditioning for solving non-symmetric linear systems, and highlight the importance of carefully choosing the parameters alpha, d1, plus and d1, to achieve optimal performance. Here is a combined summary of pages 19 and 20 of the research paper. The authors investigate the eigenvalues of the matrix EN with and without preconditioner PN, for various values of alpha and n. Figures 36 illustrate the eigenvalues of EN with alpha equals 1.5 and 1.9, and n equals 127 and 511, respectively. The results demonstrate the effectiveness of the preconditioner PN in clustering the eigenvalues, leading to improved convergence of the MINRES solver. The authors then report the iteration count and CPU time for the MINRES solver using various preconditioners, across different orders of fractional derivatives, alpha 1, alpha 2, and mesh sizes n equals n1 n2, as shown in Table 3. The findings highlight that MINRES PN achieves iteration counts that are independent of the mesh size, making it the most efficient method. The convergence of MINRES PN is determined by the maximum of tan, alpha I, 2 pi, for I equals 1, 2, rather than each tan, alpha I, 2 pi, individually. As alpha 1 and alpha 2 approach 2, the convergence of MINRES PN improves due to the corresponding reduction of the maximum towards 0. Figures 712 illustrate the eigenvalues of PN1 EN for various values of alpha I and Ni, validating Theorem 4.1 and demonstrating the improved effectiveness of preconditioning when both alpha 1 and alpha 2 are close to 2. The authors conclude that their novel approach for solving space-fractional diffusion equations using AMINRES method based on multilevel Tau preconditioners is efficient and effective, accounting for the ideal preconditioner AR pioneered in previous work. The approach achieves iteration counts that are independent of the mesh size, making it a promising solution for large-scale problems. Table 3 presents the iteration numbers and CPU times for the MINRES method applied to example 5.2, with varying parameters alpha 1 and alpha 2. The results demonstrate that the preconditioned MINRES method significantly outperforms the unpreconditioned MINRES method, with reduced iteration counts and CPU times. Figures 10, 11, and 12 display the eigenvalues of EN for different values of alpha 1 and alpha 2, with and without the preconditioner PN. These plots show that the preconditioner effectively clusters the eigenvalues, leading to improved convergence. The analysis suggests that employing the preconditioned MINRES method can lead to convergence that is independent of the mesh size. This is a significant improvement, as it implies that the method's performance will not degrade as the mesh size increases. Numerical examples demonstrate the superior capability of the proposed preconditioning strategy. The results show that the preconditioned MINRES method achieves faster convergence and reduced CPU times compared to the unpreconditioned MINRES method. The authors note that the proposed preconditioner is based on the absolute value function, f, and tau matrices. Future work will focus on developing a practical and effective preconditioner for symmetrized multi-level Toeplitz systems, which can be applied to a broader range of problems. The work presented in this paper builds on existing research, including the preconditioner proposed by Dario Beni and Fabio Di Benedetto in 1. The authors acknowledge the support of the Hong Kong RGC and the Croucher Foundation. The results presented in this paper demonstrate the effectiveness of the preconditioned MINRES method for solving space-fractional diffusion equations. The proposed preconditioning strategy offers improvements in both theoretical and numerical aspects, and its development is expected to have a significant impact on the solution of related problems. Note: I have not included the references and acknowledgements in the summary as they are not directly related to the content of the 2 pages. Toeplitz matrices have been extensively studied in the context of linear algebra and numerical analysis. The references, 27, provide a comprehensive overview of the spectral and computational properties of band-symmetric Toeplitz matrices, as well as various preconditioning techniques for solving ill-conditioned Toeplitz systems. Specifically, 5 introduces an optimal circulant preconditioner for Toeplitz systems, while 6 analyzes the effectiveness of various preconditioning techniques for ill-conditioned Toeplitz matrices. Additionally, 7 presents a unifying approach to abstract matrix algebra preconditioning. Recent works, 813, have focused on the spectral analysis and structure-preserving preconditioners for fractional diffusion equations, multi-level symmetrized Toeplitz structures, and the eigenvalue distribution of special 2x2 block matrix sequences. These studies have contributed significantly to the understanding of the properties and behavior of Toeplitz matrices and their applications in various fields. The references, 1424, further expand on the topic, discussing the convergence of GMRES, the spectral distribution of symmetrized Toeplitz sequences, and the development of preconditioned MINRES methods for optimal control of wave equations and evolutionary PDEs. Specifically, 16 presents a preconditioned MINRES method with asymptotic spectral distribution theory, while 17 introduces a sine transform-based preconditioned MINRES method for Alaton systems from evolutionary PDEs. The works, 1824, also investigate band Toeplitz preconditioners for ill-conditioned Toeplitz systems, spectral analysis for preconditioning of multidimensional Rees-fractional diffusion equations, and the asymptotic spectrum of flipped multilevel Toeplitz matrices. These studies collectively demonstrate the significance of Toeplitz matrices in numerical analysis and their applications in various fields, including fractional diffusion equations, evolutionary PDEs, and optimal control problems. The research highlights the importance of developing efficient preconditioning techniques for solving large-scale linear systems, particularly those arising from ill-conditioned Toeplitz matrices. By leveraging the spectral properties and structure of these matrices, researchers can design effective preconditioners that improve the convergence and accuracy of numerical methods. Here is a combined summary of pages 25 and 26 of the research paper. Recent studies on preconditioners for non-symmetric and time-dependent partial differential equations, PDEs, and their applications to fractional diffusion equations have led to the development of efficient iterative methods. References, 2537, provide a comprehensive review of existing preconditioning techniques and their limitations. Mark M. Meerschaert and Charles Tadgerin, 25, proposed finite difference approximations for two-sided space-fractional PDEs, while Eleanor MacDonald et al. 2627 developed preconditioning methods for non-symmetric and time-dependent PDEs using domain decomposition techniques. Michael K. Ng, 28, presented iterative methods for Toeplitz systems, and Hong Kui Pang and Haiwei Sun, 2930, introduced multi-grid and fast numerical contour integral methods for fractional diffusion equations. Jennifer Pestana, 31, and Pestana and Andy J. Wathan, 32, developed preconditioners for symmetrized Toeplitz and multilevel Toeplitz matrices, as well as a preconditioned MINRES method for non-symmetric Toeplitz matrices. Stefano Serra-Capizzano, 3335, and Gilbert Strain, 36, proposed Toeplitz preconditioners constructed from linear approximation processes and a proposal for Toeplitz matrix calculations, respectively. Andrew J. Wathan, 37, provided a comprehensive overview of preconditioning techniques in Acta Numerica, 2015. These references collectively highlight the importance of preconditioning in solving large-scale linear systems arising from PDEs and demonstrate the need for efficient and robust preconditioning techniques. The methods and results presented in these references provide a foundation for the development of advanced preconditioning techniques for fractional diffusion equations and other complex PDEs. The analysis of these methods highlights the importance of considering the structure of the matrices and the properties of the underlying PDEs when designing efficient preconditioners.